All right, so what we're going to look at today is applications of differential calculus, and this is on the second set of notes that were printed for you. So make sure you grab a copy of them and pause this video until you've grabbed them, and yeah, then unpause me. So what we're going to do today is look at applications, and note that what we have done from topic 4, which is just differentiation, is we've skipped over Newton's method for approximating roots. So we'll cover that later. Hopefully I'm back at school because there's a few things I'd like to show you with it. I can do it via this method here, but it's not as strong. So we're going to skip over that and do that a little later. So just a couple of warm-up questions here is 2012 exam 1. So this is straight up dy dx of chain rule. So what we'll do is we'll just say dy dx equals, and don't be scared to do this using a u substitution or the u sub, but I think I can do this one by sight. That's 4x squared take 5x to the 3 multiplied by the inside's derivative, which is 2x take 5. And nothing else to be done with that. That's just 1 mark already. Let's just double check that one. So y equals u to the 4, u equals x squared take 5x. Dy du is equal to 4u to the 3, du dx equals 2x take 5. That multiplied by that, complete with the u sub, is indeed going to give us that. So those of you who can do that by sight, do it. But if you got that wrong, make sure you u sub that, because you make a mistake on that, you confident mathematicians out there, and you've just lost the first mark on exam 1. So yeah. All right, this one here is an example of a question I feel like has got more bark than its bite. So got nasty notation stuff going everywhere, and it will scare a lot of students off. But let's just see what it says. So we've got this cubic function. It's important to note that it's cubic, and a is where a is a negative real number. So this one here, a is less than 0. So what do we know about cubics power 3 that are negative? They start with a negative gradient, so they look like that. B and C are real numbers. Okay, P less than M less than 0. All right, so what we've got essentially is 4 numbers on the number line: P, M, 0, N, and Q. All right, now f of P equals f of Q equals 0. So that when I put P into the function, I'm going to get 0. So it means that P is an x-intercept and Q is an x-intercept as well. All right, now f dash m equals f dash n equals 0. So that essentially is saying that the gradient at m is equal to 0. So how's this going to work? What the function's going to do is it's going to come down like this and turn there. Okay, somewhere there anyway. Like what value of y, I don't know. Then what's going to happen is it's going to cut back through 0. Now, how do I know that? Because when I factor out x, I'll just do it. F of x equals x, a x squared plus bx plus c. Note via null factor law, x is equal to 0. So it does certainly have an x-intercept at 0 as well. Then what it's going to do is it's going to have another stationary point at n. So it's got to come up like this and turn somewhere up there. All right, so that's the turning point, and then come back down through the other x-intercept, which is q. And so what we need to know is, when is the gradient of the graph of f of x negative? Okay, so when is it going to have a negative gradient? So what we're going to get is a negative gradient from here to here, and a negative gradient from here to here. So it's going to be from negative infinity all the way up to m, not including the turning point, because that's where it's got a 0 gradient. And it's also going to have a negative gradient from n to positive infinity, okay, because from here it's also got a negative gradient. And so that looks like The answer is this one here. Okay, so on to what we really want to cover today, which is tangents and normals. So we've had a look at this already a bit. Let's have a longer look. Okay, so we've got a point x1, y1 on the curve. If f is differentiable at this point, the equation of the tangent to the curve is given by this here. Okay, so this little function here is useful to state the equations of these tangents. Now, when we've got the gradient of the tangent, we can get the gradient of the normal by simply doing m1 times m2 equals -1. Now, increasingly, so just be careful, increasingly in methods, they seem not to be calling it the normal, but rather a point or perpendicular to the tangent. So this is the notation that they seem or the way they describe what they're after, perpendicular to the tangent rather than the normal. So if a tangent has a gradient m, then the normal has a gradient -1 on m, i.e. the negative reciprocal of the original gradient. So let's apply it. So what we're going to do is get the equation of the tangent and normal to this curve here at the point where x is equal to 4. Okay, so the first thing we're going to do is get the derivative of that. So I'm going to say let y equal f of x, because I want to use some function notation on it. F dash x is equal to, what are we going to do? 3 to 6. That's going to be 3x to the half, take away 4x to the negative half, 3 root x, take away 4 over root x. Okay, so now what we're going to do is get the gradient of the tangent at x is equal to 4. So I'm going to do f dash 4 equals 3 times 2, take away 4 over 2, 3, 6, take away 2 is equal to 4. So the gradient at m at x is equal to 4 is equal to 4. That's just pure coincidence. All right, so now what I'm going to do is I'm going to do this. What is f of 4? Okay, so I want to find out what the y value is at this point, okay, at x equals 4. So that's going to be 2 times 4 to the 3 on 2, take away 8 times 4 to the half. Okay, that's 2 times. Now, this is the same as 4 to the half to the 3, take away 8 times 4 to the half is 2. So 4 to the half is 2, 2 to the power of 3 is 8, 8 2's 16, take away 16 equals 0. So on the original function, when x is 4, y is 0. All right, so now let's use this formula here. Y take y1 equals m, x take x1. And we're going to slam in what we know, which is we've got this coordinate here and this gradient here. Y take 0 is equal to 4, x take 4. Y is equal to 16x. No. Y is equal to 4x take 16. All right, so let's just show you what that actually means. So first thing I'm going to graph is the function f of x equals 2x to the power of 3 on 2, take away 8x to the power of. Okay, so there it is there. And what we're looking for is the gradient of the tangent at that point. Now, or the equation of the tangent at that point. And what I'll be willing to bet is when I graph y equals 4x take 16, it's going to be a line that runs along there, nicks that point there, and continues going, pretending like it didn't nick it. Y equals 4x take. Okay, I'm about to do it. 1. Let's see. There it is. All right, so perfect, exactly what it means. Now, when we get the normal, what's going to happen is it's just going to go perpendicular to that line there. Okay, so let's do the normal as well. So m1, the gradient of the original is 4. That means the gradient of the normal is going to be -1 over 4. Okay. All right, so what else do we know? That we know that it contains the point 4, 0, so it must go through that point as well, the normal at that point. And so we'll just use the same approach. Y take 0 equals -1 over 4, x take 4. Y equals negative x on 4 plus 1, I believe. 1. All right, now let's see if that's true. So if I graph this next function, negative x on 4 plus 1, there it is. Okay, so that's the normal at that point. So there you go, that's an absolute standard question there. So yeah, you can do this on the class pad as well, and increasingly this is a 1-mark question on exam 2. Okay, so make sure you're not doing all this crap if you are in exam 2 and it's 1 mark. All right, if it's on a SAC and you got your calculator and it's 3 marks, obviously don't use your calculator. We're expecting a little bit more to give 3 marks out, so make sure you do have a good look at the marking scheme. All right, state the gradient of the following. Well, this seems like it's year 9 all over again. The gradient here, m is equal to 0, because as x increases, y doesn't. On this one here, we've got m is undefined, because the definition of gradient is as x increases, and x doesn't increase. X is always the same. So we've got an undefined gradient here, not 0, undefined, very important. All right, so what we're going to do is look at vertical tangent lines. Okay, and we did look at this in the last lesson to some extent as well. So what we want to do is draw the graph of f of x and then find f dash. All right, so f of x is the third root function. So it might help you to see it like that rather than like that. Now, third root of 0 is 0. Third root of 1 is 1. Third root of 8, 6, 7, 8 is 2. So what's going to happen is it's going to swing up like this through those points there like so. Now note that you can also third root a negative number. So third root of -1 is -1. Third root of -8 is -2. So there it is there. I'm a bit shaky on this thing here. You guys got to do a better job on your notes, and you're drawing directly on a Cartesian plane, whereas I'm drawing on a pad here next to the computer. So it's hard to do. So again, I'm making excuses, but it's just hard to draw a decent graph there. All right, now we want to get the derivative. F dash x equals, that's going to be 1/3 x to the -2/3, or 1 over x 3 to the 2/3. All right, now there's one that's unfinished. Okay, so sketch the graph of it. All right, so what this is one of those situations where we've got what I call an unfamiliar function. All right, so we don't know what really this thing looks like. Like if you pass me down the corridor and go, hey, Mr. Miller, this one here, tell me what it looks like. I'm going to say, hang on, you got to give me a sec on this one. Now, what I think is going to happen, so this is f dash x equals 1 x, or just, let's just go x over. That's wrong. Okay, that's wrong. So the derivative is actually 1 over 3x to the 2 on 3. Okay. I had the x somehow stuck in the numerator, and I just shifted that down to the denominator. So my bad. So let's go 1 over, I'm going to rewrite it as 3. Now I'm going to write it as the third root of x all squared. All right. Now, why third root? Well, I know something about third root is that you can feed third root any value of the real number system and it'll third root it. It doesn't care. Negatives, positives, it doesn't care. 0 doesn't care. All right. When you square a negative number, so should this come out negative, it's going to come out positive. okay? So what I believe this is going to be, in inverted commas, and again, don't tell your tutors or anything like that that I use this word and like it's a mathematical term, but I call this in my mind truncacy. It's sort of truncacy, okay? So remember, a truncus is 1 on x squared. And this is going to have very similar behavior, albeit this third root thing in here is going to change a little bit about the way it looks, but not much. So it's actually just going to look like this. And that's all we're really after for a sketch of f dash x. So notice that I'm really not including anything else. Now, what else? Well, it's got this asymptotic behavior as x approaches 0 from the left and the right. So what we're going to say is we've got this vertical asymptote at x is equal to 0, which essentially means for my derivative, which I did up here, we're going to say where x is not equal to 0. Okay, let's just confirm I'm right. So I'll grab that graph. So let's sketch y equals x to the 1/3. So there's my third root function. And to graph derivatives in GeoGebra, it's really easy. You just do graph of f dash. And there we go. We've got our truncacy sort of behavior, okay, where the typical truncus is y equals 1 over x squared. So there's our standard truncus. So the behavior is, as I say, truncacy. All right. Vertical line has an undefined gradient. A function will not have a tangent at a point where the derivative function has a vertical tangent. So like the one before. Okay, so we've got this, which is y equals x to the 1/3 to the 2. Okay, so this is again an interesting function here. So they do give us these ones quite often in methods. All right, so this again is third root squared, third root of x squared. Now, what do we know about third roots? Well, let's put some positive numbers in. So it's going to be like when I third root 0, we're going to get 0. 1, third root is 1, 1 squared is 1. That's that value there. Third root of 8 is 2, 2 squared is 4. 6, 7, 8. That one's going to be 4. There. All right, so it's going to do that. Now, what happens on this left side? So we saw that last time it sort of went like this. Now, what does this squared thing do? Well, if you can see what it's going to do, it's going to flick this so it's symmetrical about the y-axis. So what should happen is that there should be a point there. Now, how does this work? -1, third rooted is -1, -1 squared is 1. -8, third rooted is -2, -2 squared is 4. Okay, so there's our function. Okay, make sure you label key features. 0, 0 is the only key feature there. Forget the name of that thing there. I think they call it a cusp. Okay, so don't Google it and prove me wrong. I don't really care, but I think they call that a cusp. It's not gonna be a question. You don't need to know what it's called. You just need to know what it looks like. Now they want us to do f dash. Okay, so the gradient. Right, so let's find f dash x equals 2 on 3 x to the 2/3 take away 3/3 is -1/3. F dash x is equal to 2 over 3 x to the 1/3, or 2 over 3 third root of x. Okay, so what is this one? Okay, so 0, 3, 0. I think it's going to be kind of hyperbolic, okay? So that's what I think this one's going to be. So why do I know that? All right, so let's do a number very close to 0. So a small number when third rooted is going to be small. Multiplied by 3 is still going to make it small. 2 divided by that number. So it's going to be hyperbolic. That's what's going to happen. Now, let's take a small negative x value. When I third root that, it's going to be a small negative value multiplied by 3 is still going to be small negative, which is going to go into 2 a bucket load of times, which gets negated. So it's going to be hyperbolic. Right? Don't worry too much about the graph itself and the actual dimensions. Worry about the shape. Let's just do it. So I'm going to just pull up a new graph window, drag that across. So f of x equals x to the power of 2/3, I think it was. So there's our cusp. And f dash is this hyperbolic kind of graph where the standard hyperbola is y equals 1 on x. So there's the standard hyperbola. It's not far off, actually. Right, so let's just finish up our derivative where x is going to can't be equal to 0. Why not? Because it's a divide by 0 error. But the other reason is as we get increasingly close to 0 here, what it's going to do is, remember we've got a tangent running along here. Tangent's going to get steeper and steeper and steeper until we get a vertical tangent. Vertical tangent has an undefined gradient. Therefore, it is not differentiable at x is equal to 0. So we say you're not allowed to use that one. Oh, this one. Okay. One really similar to this came up on the SAC last year and it was absolute shambles. Okay, so these are really standard style questions. All right, so there is a formula to kind of doing these. So let's just go through it nice and slow. And why is it scrolling? Okay, so yeah, let's just do this one. So follow this formula or this method and this problem will be the same every single time. Okay, so we've got y equals x squared. And what we want to do is we want to get a tangent line to that graph, but it also has to run through 3, -7. Whatever reason we want it to run through this point. So we want to get the tangent. So it's going to be like up there and kind of like down there somewhere. It's a bit closer, obviously. Right, so we're going to get 2 points that are going to run through here, somewhere up there and somewhere across there. All right, now how does this work? We're going to say let y equal f of x. Now, what I'm going to do is get the coordinates of the point where this is going to happen. So I'm going to say it's going to happen at point A, i.e. I don't know where it happens. So the x value is A, and what I'm going to do is do f of A. Or A and f of A is simply going to be A squared. Right, so it's got to go through that point there, or the coordinates there, and it's also got to go through 3, -7. Now, what's the gradient going to be? Well, I don't know. Okay, I don't know what the gradient's going to be, but I know I know calculus, and I know that calculus gives me gradients. So what I'm going to do is dy dx, or f dash x equals 2x. And why don't I get the gradient at point A while we're at it? So f dash A is going to be 2a. Right, so now I've got everything essentially that I need. So I'm going to use this. Y take y1 equals m x take x1. Now, what are my y values? Well, I've got a squared plus 7. That and that. Our gradient is 2a, and x is going to be a take 3. Okay, so now you notice here that we've only got the one variable to solve for. So when I solve this for a, I'm going to get my coordinates. Okay, so let's expand this out. I've got 2a squared take 6a a squared plus 7. That's going to be 0 equals a squared, take 6a, take 7. Okay. I think that's right. Yep. 0 equals a plus 1, a takes 7. A equals -1, a equals 7. Right, but not done yet. So what we're going to do is put this into our kind of unknown coordinates of the tangent. So if a is -1, then one of our coordinates is going to be -1, 1. All right, that's going to be this one here. And the other one is going to be high, as the diagram suggests. So it's going to be 7, 49. All right, so find the coordinates of the points on this that goes through this. These are your coordinates. All right, and again, let's just check that out. I think it's worth having a look at that on GeoGebra to kind of see what it means. Okay, so my original function is y equals x squared. And what we're going to do is, just enlarge this a bit. I'm just going to plot the point 1, -1, 1. Okay, now GeoGebra's got this cool feature, well, I think it's cool, where what we can do is run a tangent. Okay. I'm also going to plot the point that we wanted it to run through, which is 3, -7. Now, if I've got this right, what I'm going to do is ask GeoGebra to draw a tangent at that point there. And what I'm willing to bet, okay, and if it turns out wrong, I'm going to re-record this video anyway, but what I'm willing to bet is the tangent is going to run along this point and bang, it's going to go exactly through there. Let's check it out. So tangent, I've selected it, yep. So tangent requires you to select point and function. Here we go. Bang, beautiful. Okay, so there's one point. Now the other one was 7, 49. Which is way up there. There it is. All right, so what I'm predicting as well is I'm going to run a tangent at that point to this function, and it will also run through this. Let's see. Select function, select point, bang, tangent goes through there. Beautiful. Okay, so really common problem. It's high end. I go through it every year. Students kind of understand it and then seem to stuff it up in the sack. So yeah, like get your hands on as many of this type of problem as possible. They are regular. Right, there's your work for today, girls, which is 10A. So get that done and I'll jump online and yeah, give you a hand with whatever you need.